Hello, this is Ali again, and I'm going to talk about statistics for data science. So today we're going to review some concepts that you've heard about, and we just want to know how we could use that and leverage those information for data science. So some of these concepts are population, data sampling, the data distribution, and how to perform a hypothesis test. So first, let's talk about sampling and the population. So in general, um, when you take a look at the large like samples of data, like all the larger body of measurements that we have, for example, when we're looking at the average like age of Canadians or average height of Canadians, then it's impossible to go and try to ask everyone to see what their height is currently, and even the census is happening every 5 years. But if you want to get that information, instead of asking every sample of the population, you could just get a smaller sample of that population, and then you can try to use that sample to predict the behavior of that population. So the population is the whole larger body that we want to get some measurements from, but because it's not possible, we draw a sample from that population and we use that information to basically like predict the behavior of that larger population. So we get from sample one or many samples and get to the population information. For example, if we have the like for the whole Canada, um, want to get the average height of the people, then instead of just going and ask everyone, we get some samples from maybe the Eastern Canada, Central Canada, Western Canada. So we and also from the North. So we get some samples from different places, and there are many ways that this could go wrong. So, for example, if you just get samples from a specific city, like from, I don't know, Toronto, and do not consider different cities and areas and regions, then you have not performed random sampling of the population of the Canada. You perform probably random sampling of the population of the Toronto area or Ontario. So proper sampling is very important, and you're going to learn some ways to do that. So in simple random sampling, you get a sample of n elements from a population of size capital N. And this is possible when each sample that you get from that population is actually has the same chance of getting selected. So if it doesn't have the same chance, then either something's wrong with your sampling or you're using a specified type of sampling. So you usually perform sampling based on a sampling plan. So the sampling plan, we have many of them. Some of the major ones are a certified random sampling, cluster sampling, and systematic random sampling. So let's talk about some of them. So in stratified random sampling, instead of getting a random sample from the whole population, you first create some groups called stratum. So each stratum, like group of like classes of individuals or people from the population, each of those stratums may have a specific category. For example, some of these elements, this is like one group, this is another group, this is another group. It could be from a specific geographic region, it could be of a specific class, And it doesn't matter, it's not necessarily for like human beings. Like if we're looking for sampling from some image data, from images of flower, from images of animals, all that, you want to make sure that you identify some of these strata before, and then use one of these two methods to actually draw samples from that population. One is unified sampling. So in unified sampling, you take a look at each stratum, and then what you do is that you just take a certain amount of samples from each of them. So in this case is the proportional one, like this example that we have. So if we were using the unified stratified random sampling, we would get one from this group, one from this group, and one from this group. So it's unified among all the groups. In proportional stratified sampling, what you do is you actually consider the size of each stratum and then select some samples from it based on the size of the that subpopulation. So here we have like 3 from the white group, 6 from the black group, and 3 from the gray group. And if we use proportional sampling, the best way to do that is to like select one of these 2 groups and 2 of these groups. So this is a stratified random sampling. So if you want to get more samples, then you double this amount. So this is how you could perform a stratified random sampling. And this is a great way if you want to make sure that your data is not like somehow necessarily biased, or if sometimes it introduces bias. So you have to be careful. If there are not a lot of representatives from each group, you may consider unified sampling. If there are not I don't know, like there are some minority groups in your population, you want to make sure that you select some of them. So if, for example, there are some, one example is that if there are some disabled people in a university and you want to, like in a class, there might not be many, there might be a few. So if you just do random sampling, you may lose that group entirely. If you're selecting 3 students from 1,000 students and you're going to use just random sampling, there's a high chance that they will not get selected. Or you may use proportional sampling, but you could make sure that at least one individual is selected in that proportion. So you want to get the floor of that sampling. Because if there is only 3 out of 1,000 and you're getting I don't know, 10% of the population, like 1% of the population, you get 10 people, there's a high chance that a specific group is not selected. There are some other ways to perform sampling. There is one-in-case systematic random sampling. So in one-in-case systematic random sampling, what you do is that you want to start with the first k element. So you just select one of the first k element that you have. For example, if k is 10, you select one of the first 10 elements from 1 to 10. For example, number 6 is selected. And then after that, you go and select you just add k to the base sample, and then you select every k element. So 36, 46, and so on. So you just select these, but this only works if you have an ordered population. So you have an ordered population based on a specific criteria, and then that is going to be the ideal population for you to start getting systematic sampling. There are some other like sampling, like for example, judgment sampling. In judgment sampling, what you do is you use an expert, or the researcher itself decides how to select some samples. In that, I don't know, like disabled student example, a teacher in the class or maybe someone in a specific community tries to make sure that everyone is included, and maybe you could do that using judgment sampling, or you could put it into a coda sampling. So in coda sampling, for example, if you were looking for one representative from each department, then you could just ask each department, no matter the size, that, well, we need only one representative from your department. There might be some departments with a lot of students or a lot of faculty members, and you just get one. There might be smaller groups, and they will represent one. So either you can create codas, or the researcher could have used some judgment. The cluster sampling that I've talked about it here, is just similar to the random sampling, but instead, if your data is divided into clusters, so if you're, let me show it on this example. If your data is divided into some clusters of this sort, this is one cluster, this is another cluster, then you randomly select one of these clusters. For example, this one will be selected. So that will be a whole cluster of samples that will be selected. So there are some frequent problems, frequently occurring problems, actually, frequent problems in these simple surveys. One is non-response. So if not all your random samples are responding to the survey, so select a few people to get the survey off, and then they will not respond to your survey. So non-respondent is one major problem, that you've carefully selected a lot of people, but they're not answering. Another issue is under coverage, or somehow it's similar to bias sampling. So if you do not select your population randomly enough, or you're not using stratified sampling, or you do not put enough coda, then the data set that you maybe use may not include some groups of people. So some specific groups may not be there. For example, if you're just that happens a lot, that when we get surveys from the computer science, in the computer science department, we ask students in the computer science department, and the data samples are usually from computer science students. And we're asking them, okay, how good are you using, I don't know, LaTeX or Microsoft Word or a specific software? Because they're computer science students, they're more familiar with the just computers in general, and that will create some bias. We cannot use that data and assume that is the data that was selected from all the students from the university, So that's one major thing to consider. Another issue is wording bias. Sometimes your questions the wording of the question could be a little bit confusing, and different people might not include the information accurately, and you need to make sure that that is also considered and covered. So the main reason that we do sampling is to estimate the population characteristics, like what is the mean, what is the variance, what is the different percentiles of that population. So to answer those questions, we get some samples, and then we try to estimate those parameters of a specific population by using some techniques like point estimation, and maybe adding some confidence intervals to really estimate that. So again, there are many methods, but one of the interesting things that will help you to understand how sampling works is Monte Carlo simulation. Go and check it on the YouTube. It's a very interesting scenario that enables you to actually try to estimate the um, pi, like the value of pi, by creating a piece of paper, drawing a circle on it, and then randomly, I think this is not a great drawing that I have here, but if this is going to be a circle, kind of, then if you just close your eyes and then try to randomly put some dots here, and then try to count the number of dots that are outside of that circle, and there are some dots that are inside of that circle, and then you put them into the equation. The more samples you have, it gives you a more accurate value for pi. So just by adding some, like randomly putting some dots there, the more you do, the more accurate you get the actual value of pi. So what I wanted to say is that what we want to do is estimation, and the more samples you have, the better the estimate of the actual population. So that's something that you should actually try to consider. So now let's talk about how we could use these estimates to understand the distribution of the population. So just as a reminder, the distribution of an event, like, or any data, is made of all possible input values. So if there are, if this is the, I don't know, like maybe credit score, if this is the credit score of different individuals, and like most of the individuals have a credit score of 500, and a few of them has a lower, like a higher and lower ones, it's kind of different, like in a different measure. Then if you get all the different credit scores that people have, you may get to this kind of distribution that if you try to estimate it, you can actually estimate it using the mean of that population, or mu, and also you could get the standard deviation of the population as well. And just these two parameters, this estimated parameters, can give you the distribution, the possible distribution of the whole population. So so the density of the probability of occurring, like probability of one event occurring or one value to be found in a population, can be described by a function of f of x, and this function is actually called the probability distribution for that random variable. So I put that function like one famous function, which is called the normal distribution here. So this is the formula for the normal distribution. The formula for normal distribution is actually this, and depending, it actually has two parameters. This function has two parameters. One is sigma, which is the standard deviation of your samples, and then we have the mu, which is the mean of the sample. So we actually estimate the mean and the standard deviation based on our samples. So we get those samples, we calculate the mean of the sample, so we estimate mu and we get estimate the standard deviation, and then we could draw these standard normal distribution plots here. And you could see that if the mu is 0, depending on the value of the standard deviation, and this is actually the variance. So so based on that value, you can get a different distribution. But if you look at all of them, the look of a sample distribution is like a bell-shaped, even kind of a diagram and a function. If the mu is different, in this case, in the green case, this one, you can see that mu is -2 and it's basically just shifted to the left a little bit. So the standard deviation actually changes the width and the spread of that distribution. So why do we care about random distribution? Because it's useful to describe many data sets. If you look at a lot of different data sets and a lot of different data in general, you will see that most of the data, natural, normal occurring data, tend to have a normal distribution. And it's assumed in many statistical models and techniques. So they say that, well, assume that your data is distributed normally, then we do this. So if your data is not normal, it's not a bad idea to try to make it normal by applying some transformation. We talked about that, like get the log of or a square root of your data if it is skewed to the left or right. And yeah, that's going to be the like kind of the distribution that we're going to use. So one way to get that estimation, to get the estimate of this distribution, is point estimation. So the point estimation is actually trying to get the mu and sigma by using the mean, like getting the mu by getting the mean of the samples, and using the like sample standard deviation S, using this formula, and then you just get the square root of it. So this is the variance. So what are we talking about here? We're talking about the fact that these are the actual, like the sigma and the mu are the actual, we assume that that is the actual parameters of the population, but we don't have the whole population. So we estimate these variables. And the estimation is, using point estimation, is that we just try to describe the whole population by two values. One is the mean, and also the other one is the standard deviation. It is also helpful to point out how sure we are about an estimation. So if you're doing point estimates, it makes a difference if you use 1 sample or 100 sample or 1,000 or 1,000,000 sample, right? Because the more samples you try to get and using your estimation, the more accurate your estimation is, and you get a better picture of the whole population. So we use confidence intervals and try to formulate this in a way that if you're looking for a center level of certainty or confidence, then you could give it to you could use give it to the t-distribution, use the t-distribution table, and mention what is the accuracy that you're looking for. For example, if you're looking for 95% confidence intervals, which means if you repeat this experiment for many times, 90% of the intervals will be in that range that you calculated, will have the same mean and standard deviation that you have. So if you're looking for example, 95% intervals, you choose like alpha to be 5%, you put it in that formula, and it gives you the actual confidence interval for your point estimation. Usually what happens is that let me tell you this and then I'll talk about that. What that means is that when you put that as 5%, 90% of the that means the 90% of the population of that estimate that you have probably falls in this area, and then half of that, like 2.5% of the data distribution, could fall into either side of that distribution. And we're using this to do something very interesting, which is a hypothesis testing. So in hypothesis testing, sometimes you want to know if the mean of one population is different than the mean of another population. And what would you want to know that? You would want to know that because if you claim something, if you claim that you have a better approach, you have created a new method that increases the youth health, you have created a method that reduces the number of people with, I don't know, drug abuse. If you say that you have created a method which is faster in terms of, I don't know, for example, if you're creating a search engine, you say that you claim that I've created a search engine which is faster than your search engine. And when you look at the values, you will see that yes, it is faster by half milliseconds. And then someone says, is that even a significant difference? So when someone asks you about significance of difference between two populations or something that you devised, you need to prove that by a level of certainty. So usually, like by default, that level of certainty is 95%, the same thing as we mentioned. And the way to actually prove that your population is different from another population is that you can use a t-test. So in t-test, what you do is that you get a null hypothesis. So first you assume that the mean of the two populations are actually the same. And then you try to, you're trying to like reject the, like, depending on what you want to do, you choose this differently. You find another hypothesis, which is an alternate hypothesis. And that hypothesis says that these two values are actually different. So if you cannot prove that, you cannot prove the alternate hypothesis, that means that the population are actually the same. If you can prove that the alternate hypothesis is actually true, then that means that these two populations are actually different. So depending on what you do, you just use this test in a way that you like. And this is what kind of we could show. Like, this is an example that we have here. You see we have two populations. It looks like they are the same. You just want to make sure that they are the same. You do a t-test, and then if the you cannot prove that they're not different, then they're the same. And in this case, this is another case, you have two different populations that you could use. We have other tests that work on more than two populations. So for example, if you are going to compare more than two populations and you want to test to see if the means of k populations are equal, you could use ANOVA. And the null hypothesis is that all the means are the same, and the alternate one is that, well, for at least one pair of those populations, the means are not the same. And you see, in all these cases, we assume that the populations are normally distributed. Also here in t-test, we assume that the populations are normal distributed. So these are some actual tests. There's also a Wilcoxon rank-sum test, which uses the order of the observed sample, and it doesn't have any normality assumption. It's non-parametric. So these are some of the ways that you could use to see whether whatever you proposed, like, is different from the previous version of something. If someone asks you, if you made something better and someone asks you, is it a significant improvement or not, then you're going to prove them that it is significant by using a t-test with a certain interval and saying that, well, it is different actually. So let me give you an example. Imagine in a company, there's a manufacturing process that has been producing parts with a mean diameter of 10 millimeters. So they had some like parts that they were producing with a diameter of 10 millimeters. And there has been a standard deviation of 0.2. So some of them could be up to 0, like kind of 0.2 or 9.98. So the range of the size has been, the diameter has been something around this. But someone suspects that the manufacturing process has shifted. So it's not like that anymore. It's probably producing, I don't know, 99 and then with a little bit of shift. And but how can we know? How can we know for sure that this is the case? Because if you take one of those parts and it is 10.3, it is still possible that this is within that range, because that's a standard deviation, and it could be, you know, like when you look at the random distribution, we kind of look at this area, and there could be always some outliers. So if you keep picking and picking and picking, and you just start getting some samples, and it seems like most of them are around the, is like they have a different mean, then that could be the case. But statistically, you cannot say for sure until you get some samples, new samples, and use a statistical test like t-test. So the approach is that you assume that the process is producing part with the same thing. So you assume that the means are the same. That's the basic assumption. Sample, and then we get the sample of the sum of the parts. If the average diameter of these parts is significantly different than 10, by significantly different, it means like, I don't know, you define that 95%, 90%. So you choose a different alpha or p-value. If they are significantly different, then we conclude that the process has shifted. If we cannot prove that they are not different, they are different, then we conclude that the process has not shifted. So we assume that they are the same. We try to prove that they are not. If we fail, they're actually the same. If we do not fail and we prove that they are different, so they're different and the process has shifted. So sometimes the significantly determination is difficult to kind of determine and to be determined. And like if we assume that the process has shifted, but it has not, and we just assume that by error, what are the costs? The costs could be a lot. Like we could change a whole process, spend $1 million because we thought that the process has shifted, but it hasn't. So that is going to be very important. So these confidence intervals are going to help us in that process. So again, remember, if you have a new idea, if you have something that you want to prove, you need to make sure that you prove that whatever you propose is actually significant. If you have any questions, let me know, and we'll continue to the feature engineering and model planning after these. Okay, take care.